Who's ready for some calculus? All right, next part, we are doing center of mass, but instead of separate individual particles, we're going to do a single object, which sometimes you'll hear called a continuous body, but it's just one thing. All right, to find the center of mass of a continuous body, we still need to divide our position times masses by the total mass, but instead of summing up our individual point masses times their positions, because we just have one thing, we need to essentially, so we have, say we have this continuous body, we need to cut this thing into a bunch of tiny little pieces, and each piece has some mass and is some position away from our reference. And we're going to add all those pieces up, which, as you might guess, that means we're taking integrals. So we're going to integrate the position of each of those tiny pieces with respect to mass. So we're essentially saying, well, this amount of mass is at that position, this amount of mass is at that position, this amount of mass is at that position, and then we add all those up. All right, so that is the equation we use. And we're adding up all the positions with respect to the mass of those tiny little pieces. The first example we're going to do uniform and then non-uniform. Now this is the only shape you need to know how to do. So uniform, that means it has the same density throughout. Thin, that means we're only worried about essentially one dimension. So we're considering it so thin that it doesn't have any depth or height, I guess. Yeah, it only has length, so that's handy. So say we're gonna think about our meter stick. So we're just gonna, kind of looking at our meter stick from the side, and I want to know where is its center of mass. Which we're going to consider a uniform thin rod. What's happening? That looks great. So obviously you're like, Ms. Lang, it's at 50 centimeters. Well, you need to prove it. Oh, that's cool. So we have our meter stick, and we're going to set one end of the meter stick as our 0, as our reference, and the other end is just, we can just call it L for now. Obviously it's 100 centimeters, but we'll get there. Couple things we need to know before we jump into this. One is the term for linear density. So this is, since we're only in one dimension, we don't need volume because that's far too many dimensions. Okay, so we don't need, when we do density, we're not going to take mass over volume because we're only dealing in one dimension. So instead, linear density has our symbol lambda. Okay, we have to share that with wavelength, I guess. And that's the total mass of the object divided by the length of the object. But this is only true if it's uniform. So you can only use the total mass over the length if it's uniform density. Now we're going to also say, well, that could be, we could say this dm over dx. So it's essentially the mass, okay, calc style derivative of the mass with respect to position, which we can rearrange. We're going to do some illegal calculus here to say, okay, dm is equal to lambda dx. Okay, so we need to know both of those things in order to make this math happen. Okay, now we can actually start our math. So starting with our equation, the limits for this integral we're adding up all the positions with respect to their mass from one end of the object to the other. Now, if you know the length of the object, you'll plug that in for L. Because that's how far away the other end is. Oh, that looks great. Thanks, computer. Object. You gonna keep that? All right, good job. Okay, so now, instead of this dm, because I want to be able to integrate this with respect to the position, because these are position limits, not mass limits. So I'm going to kind of change this integral and say, well, dm is equal to lambda dx, which I got from this equation up here. So I just rearranged lambda is equal to dm over dx, which is, again, illegal calc. I arranged it over here. So I'm going to substitute that in for dm. So that gives me 1 over m. Now I'm going to integrate lambda dx. So now I can use actual positions for my limits. But I'm not quite done yet. For this lambda, okay, I don't really know what to plug in for that. Oh, but I do, because lambda is equal to m over L. So these are all the substitutions you're going to have to do before you even start your calculus. And now you can actually do the math. So this is where I'm left. And you can see here, so we have a total mass here and a total mass here. Those are just going to cancel out. Now, since the length of the rod is a constant, I can kick it out of the integral. So now since my m's went away, I just have 1 over L. And when I integrate x, I get x squared over 2. And I'm going to evaluate that from 0 to L. Okay, so I'm going to plug in L for my position. That's where you plug in your limits, is into that x. So I have 1 over L times L squared over 2 minus 1 over L times 0 squared over 2. Obviously, that's going to go away and be 0. So one of these L's will cancel. So I'm left with essentially 1/2 L. If our meter stick is 100 centimeters long, then the position of my center of, oh my gosh, I'm going to punch you. Why? Guys, it's halfway through it. It's at 50 centimeters. My computer's dumb. Okay. You get it, though. The position of the center of mass is 50 centimeters. Holy cow. Okay, something that you already knew, but now we proved it with the math. All right, so that's all good and fun, but now what if we are non-uniform? Okay, I'm going to go to the next video for that one.